Hello 1020 class. This is some of the new material, section 5.2, and we're going to talk a little bit about logarithmic functions, or at least do problems for log functions. So if you looked over the PowerPoint slides, you know that the logarithmic function is the inverse of the exponential function. So just a brief review or explanation. If I start off with an exponential function, say f of x equals b to the x, and I want to find the inverse of this thing. Well, we know to go through the steps, the first thing you do is replace f of x with a y, and then you switch around the variables. That's what I would normally do. And then I solve for the new y. Well, the only problem is we don't know how to algebraically solve this thing for y using any of the tools that we have at our disposal. But the original function is 1-to-1, because b to the x either looks like this or it looks like this, but in either case it passes the horizontal line test, so it actually does have an inverse. So the inverse exists, but we can't explicitly express it. So what we do is make up some notation to represent the inverse function, and that's what the log function is. It's the inverse of the exponential function, but that's just notation for the inverse of this function. And the way you read this is log x to base b. So having said all that, and that's just a quick explanation of the log function, what it means, I really want you to look at the slides. I really want to devote these videos to just problems. Let's do number 1. It says write the log equations in exponential form, and it says y equals log x to base 3. Okay, so here's the way I like to do this. This is in log form because it's got the word log in it. But if you want to change to exponential form, start with the base of the logarithm, and that's that little number below the log. And then form a little circle. 3 raised to the y power is equal to x. So that's how you change from log form to exponential form. Alright? You go in a little circle and you form the bottom of the circle first, and you start with the base. So let's do another problem. Number 7. In the book, which is really number 2 on your list. And this one says write the exponential equations in log form. 32 equals 2 to the 5th. So it's in exponential form because it's got an exponential expression in it. So how do you change it to log form? Well, I will show you. It's a similar trick. Write down log first. Now notice the base of the exponential expression is 2. So you would make that the base of your logarithm, and you would go in a little circle. Log base 2 of 32 is equal to 5. That's how you can go in the other direction. So in either case, you start with the base and you go in a little circle, and you always form the bottom of the circle first. It's just a trick, really, a gimmick for converting from one form to the other. All right. So if I wanted to make up another example, I could say 2 to the 4th is equal to 16. I know that's a true statement. Well, the base is 2, so say log base 2 of 16 is equal to 4. It's just a little gimmick for converting from exponential form to log form. And you do something similar in the first problem. Well, let's move on to number 3, which is number 9 in the book. It says evaluate the logarithms. If possible, round each answer to 3 decimal places. So number 9 from the book has 3 parts. Excuse me. A is log 7. All right. Now, I haven't mentioned this before so far, but anytime you see a log expression with no base, it is understood to be base 10. All right. So that is log base 10, but usually you just refer to that as a common logarithm. So you're supposed to know that that's base 10, that it's understood to be base 10. But fortunately, you can evaluate this with a calculator, and I think that's what they want us to do. So I'm going to start with the Inspire, for just a few of you that have this. So let's turn it on. All right, and I want to evaluate log of 7 to base 10. So let's switch to calculate mode because we're going to do a calculation. All right, and you might notice that right above the 10 to the x button, which is right there, you see the word log. So I want to get to that log, and that's the common log because it just says log. So to get to that blue log, I've got to go control 10 to the x. So let's do that. And when I do that, it's a little hard to see, but your calculator gives you something like this. I wonder if there's any way for you to see that. It's a little hard to see. But your calculator will display something like this. It'll show log, and then you'll have empty parentheses here and maybe empty parentheses there. So you've got to enter a number both here and here. Well, you might have to enter the 10 manually, because that is a common logarithm. So on this calculator, go ahead and enter that 10 manually, and then just put a 7 there and press enter. So try that with your calculator if you have the Inspire, and I'll tell you what I get. So I end up with this number to 3 decimal places, 0.845. All right. And we're supposed to do this to 3 decimal places. So just quickly on the other calculator too, it's almost just as easy. This one's a little easier to see. Now notice on the Inspire you can change the base to whatever you want. On this one you are only allowed to use base 10 or base E. So there's your log key right there, you can see on the left hand side. So you just have to hit log 7, close the parentheses, enter. So there's your 0.845. I think most of you have that calculator. So that is the common logarithm of 7. And that's part A. Let's do part B. It looks like it's some more calculator work. Natural log of 86. So I've got to say something about this too. Now anytime you see that ln, that means log base E. Alright, that's the base. And remember, E is just a number in math. It's about 2.7. So it's an irrational number. It goes on forever. There's no pattern to the digits, but it's about 2.7. And it pops up a lot in mathematics, including logarithms. So how do we do that with a calculator? Well, let's do it with TI-84 first. All right. So notice right there is your natural log key. So just hit ln. All right, it's right there. And then just ln 86. Close your parentheses. Kind of easy. 4.454. All right. Well, let's do it on the other calculator real fast. After that, I don't think I need to do it with the calculator again because I think you can see how to do it. So how do we do it on this calculator? Well, notice that you have an e to the x button right there. It's a little grainy there, a little fuzzy, but right above that e to the x is an ln in blue. So you just have to go control e to the x, and it'll say ln on the screen. You can't see it, but just put an 86 between those two parentheses, and then enter. And the calculator does display 4.454. All right. So that's how you do it on the Inspire if you have that calculator. Oh, by the way, that is called a natural logarithm. Anytime you see that ln and the base is e, that is called a natural logarithm. So you have a common log when the base is 10, and natural log when the base is e. So I think I'm going to skip part C of number 9 because it's in the book, which is really number 3 on your list, because it's similar to the rest of them. Let's do number 4, which is really number 11. Find the value of the logarithms without a calculator. And this one is log 32 to base 2. So there are really 2 ways to solve these kind of problems. I'm going to try to show you the easy way right now. You can interpret a logarithm as the number that you have to raise the base to get the big number. So in other words, 2 raised to what power is 32? The answer is 5. All right. And the next one is log 27 to base 3. So what do I have to raise 3 to get 27? The answer is 3. Next one is log 625 to base 5. That one's a little trickier, I guess. But I'm guessing if you raise this thing to the 4th power, then you're going to get 625. So it's probably 4. Let me just make sure. 5 to the 4th power. Yeah, that is 625. So that looks correct. All right. By the way, let me give you another reason why that works. This is the way I used to do these problems. Just set it equal to y, convert it to exponential form, and then solve that exponential equation. Well, you can solve exponential equations by making the bases the same. I don't know if this makes it easier or not. So I know 625 is 5 to the 4th power. You can show that there's a property that says once the bases are the same, the exponents have to be equal to each other. So y has to be equal to 4. But what is y? It's the log of 625 to base 5, so that's how I get a 4 there. That's the other way to do it. But the first way is probably easier for most of you. Well, let's move on to number 5, which is 23 in the book. And it says, use the properties of logs to evaluate the expressions. Log of 10 raised to the 14th power. So there are any number of ways we can do this problem, and I'll try to do it the way that they probably intended for you to do it. There is a property, and it's probably mentioned on the slides too, that says if these two numbers are the same, then this whole logarithmic expression simplifies to just the number on the far right. That's one of the properties that they mention in the section. All right. So in this case, notice that the base is understood to be 10 because there is no base. It looks like a common logarithm. So the number on the far right is just 14. So that's all you do on that one. Easy. Now this one is number 53 from the book. It says if an earthquake has an intensity 25,000 times I0, what is the magnitude of the earthquake? So 25,000 times I0 is the intensity. All right. And they're looking for the magnitude. Well, let me give you the definition of the magnitude of an earthquake. And I think they usually use an R there. It is this. It's the common log of the intensity of the earthquake divided by the intensity of an earthquake that is very, very small, a barely discernible earthquake. All right? And that's what I0 is. So I0 is just some known number, and somebody decided, okay, well, an earthquake that has this intensity is so minor, we're going to consider that the smallest possible earthquake intensity. Well, this is the measurement on the Richter scale. So they're basically saying the intensity of the earthquake is 25,000 times I0. Well, the intensity is I. So all you have to do on this problem is just replace that I with the 25,000 I0. Notice your I0s cancel. So you're going to end up taking the log of 25,000. And yeah, that is the common log. Let's use a calculator. And I get 4.4 to the nearest tenth. They don't really tell us how to round this thing, but it's about 4.4. So you always hear about earthquakes in the news. Some of the worst earthquakes are in the nines. The worst earthquakes in history are 9.2 in that range. So 4.4 is not too bad. Well, let's move on to the next problem, which is number 7. That's the last problem on the list. It's really number 55 in the homework, or in the book. The Richter scale measurement for the southern Sumatra earthquake of 2007 was 6.4. So on this one, they give us the Richter scale measurement of the earthquake instead of the intensity. Find the intensity of this earthquake as a multiple of the I0. So we're just going backwards. They're saying here's the Richter scale measurement, find the I, instead of being given the I. And they want us to write the answer as a multiple of I0, which is probably a good idea, just because we don't know what I0 is. But for most of these problems, you don't need it. Okay, so how do we do it? Well, replace the R with a 6.4. And the trick is just to convert this thing to exponential form. So you might have to write in the little 10 there and then do the little trick that I showed you in the first couple of problems. Just start with the exponent, go in a little circle. 10 raised to the 6.4 is equal to I divided by I0. And notice that you can solve that equation for I by multiplying both sides by I0. So 10 to the 6.4 times I0, and it cancels out on the right there, is just equal to I. And you probably should plug that into a calculator. I think they want you to, the 10 to the 6.4. But I get this huge number. And I believe they want you to enter that entire number. I'm not sure you have to enter the I0 part. I don't think you do. So that should do it for this video. That was section 5.2.